Find the t-value such that the area under the t-distribution to the right, be careful with this book, to the right of t-value is 0.10, assuming 15 degrees of freedom. Okay, so we're going to do it with a calculator and then StatCrunch. Here's with the calculator. And yes, you will, this is new. This is new. All the calculators do not have inv-t. Okay, so find the t-value such that the area to the right of the t-value is 0.10, so the area to the left is 0.9. Degrees of freedom, assuming 15 degrees of freedom. Okay, 15. And I just want to find this t-value, 1.34. So what does this mean? This is example 2. So this is t with more in the tails. And we were given degrees of freedom 15. And it says the area to the right, this is 0.10, which means this must be 0.9. So this value here is t, 0.10, and we got 1.34. And I'm just curious now. Do we have, yes, we do have TCDF. I'm curious. I want to determine the area to the left of 1.34 because something is happening with this calculator. So the lower is negative infinity. The right is 1.34. And degrees of freedom 15. And if I don't get the area to be 0.9, then something is wrong. Okay, in this case, it gives the correct area. Of course, there is a little approximation, so I'm happy with 0.89999. I'm happy. It's 0.9. Okay, that's how we determine the t-values. Of course, we can also determine them from a table. Okay, our next step is, once we have the point estimate, which is x bar, assuming that we're talking about randomized experiment or a simple random sample, the condition of independence is coming back. Again, the sample size has to be less than or equal to 5% of the population size. And data came from a normally distributed population, or n is large. Okay, so how do I determine the confidence interval for the mean now? Okay, so let's say 95% confidence interval for the mean will be x bar minus the margin of error, x bar plus the margin of error, where E, as we know from before, margin of error. And what is the margin of error? The margin of error, like before, if you remember, in proportions, we had the margin of error z alpha over 2, the square root of p hat, 1 minus p hat, divided by n. That was for proportions. Now, the margin of error for estimating the mean is t alpha over 2 times s, where s is the sample standard deviation, divided by the square root of n. So I'm going to go back and plug it in. You have it on the paper anyway, but I wanted to show this because we're going to look at the sample size in a minute, of course. Okay, so then it's x bar minus t alpha over 2 s over the square root of n, and x bar plus t sub alpha over 2 s divided by the square root of n. Of course, with degrees of freedom n minus 1. Why? Because this quantity depends on the degrees of freedom. This quantity is the same, and it will depend on degrees of freedom. It's different for different degrees of freedom. So we're still trying to find an estimate. Like we just had that example with 95%, 90%, whatever, meaning that we are 95% confident that if we repeat the experiment 100 times, 95 of those intervals will include the true population mean. Maybe more, but at least 95 will include it. So back to example 1. We are constructing a 95% confidence interval for the mean miles per gallon. Okay. And interpret the interval. So where is my information? We determined over there. So we determined X bar to be 36.8. And we had 16, right? Yes. So N was 16, which means degrees of freedom, N minus 1, which is 15. We want a 95% confidence interval, which means this. We should always graph it. I'm going to graph it a little bit thicker in the tails because we are talking about T. So this is the T distribution, only characterized by degrees of freedom, nothing else. And 95%, this is 95%. Obviously, this is 5% in both divided by 2, 2.5% and 2.5%. And I need to determine this T. Oh, I said that I was going to show you StatCrunch. We're going to go back there in a minute. So with the inf norm with the calculator, hopefully you have that. The area to the left, 0.025. Degrees of freedom, 15. Just give me T. Negative 2.131. I forgot to look at how many, it doesn't say how many decimal. I'm going to use 4 decimal digits for now. Negative 2.1314. Of course, this one will be 2.1314. Now, I'm going to write it, but I'm not going to calculate it like this because we have a way of finding the confidence interval very nicely in the calculator. So this was my 5 and 6. Okay, and StatCrunch. So the 95% confidence interval will look like this. 36.8 minus 2.1314 times. It says use standard deviation. It doesn't have it, so I have to go back and recalculate it. Good, no problem, very easy. Okay, the standard deviation, it was 2.917. No problem. So 2.917 over the square root of 15 and comma 36.8. I don't have enough room, so plus, I'm going to continue here, plus 2.1314 times 2.917 over the square root of 15 and close the interval, a parenthesis. Am I going to do it like this? No. But I had at least to present it so you know where the information is coming from because I do have an option here. Not with this, not with this, with this. With tests. Okay, so from scratch, stat, go to tests, and try to look for one sample z t interval. One sample z interval. Where is it? A z test, no. T test, no. One proportion, no. Two sample z test, no. Z interval, t interval. Yes, that's the one. Number 8. So press enter. And I could use the data because he's already in list L1. So I could do that. Let's do both. Okay, I have the data on list L1, and I have, or it already pops up with 0.95. So I'm done, and here's the interval. It's 35.246, comma 38.354. Okay, and it gives me automatically X bar and S, and N is 16. I can do it again. Clear. Second, no, just go to tests, and I want the T interval. And this time I want to put the stats, which is the same thing. It's already entered, right? It's already there, and I'll get the same answer. If you want to convince yourselves, let's determine just by hand just one of the sides. 36.8 minus 2.1314 multiplied by 0.917 and divided by the square root of 15. You know I'm all about checking. I have to check. So the calculator gives us a better approximation because it does not truncate the 2.917. As you saw, it goes to 2.917, blah, 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 blah. But I cut it off after the third digit. And if I want to determine the one with plus, I just have to copy. So careful on that. Very close, but this is a better approximation from the calculator because it did not truncate the standard deviation of the sample. Okay, so now let's, I'm going to share the screen with you so we can do this with StatCrunch. Where is, I can close this, I guess. StatCrunch. Okay, T-stats. One sample with data. I didn't enter the data, so I'm going to use the summary. I'm going to close this. Okay. Sample mean. Where's my keyboard? Right here. It was 36.8. Sample standard deviation. So it's better with data because it will give us a better approximation, but I don't want you to watch me plug in 16 pieces of information. Sample size is 16. No, it's not hypothesis testing. Yes, it is 95. Stored in a data table. Yes, I want the output to be stored in a data table. Optional graphs. Yep, why not? I want to see that too. Compute. Okay. So, well, it didn't present it in a table as I wanted it. Oh, maybe it did. Let me see. Ah, it did. Okay. So here's the sample mean. Here's the standard error. It calculated it for us. Degrees of freedom 15. The lower limit, exactly what we got with the calculator. Perfect. 35.246 and 38.354. And now here's the graph. Oh no, I've done that last time and it doesn't show the plot. Okay, I don't know why. I'll investigate. Okay, perfect. So I am going to, where are you guys? Okay, I'm going to stop share.
If you go back and edit it and take off store in data table, it'll just give it all to you in that window that appears.
Yeah, but does it show the graph?
No, the graph still doesn't work.
Yeah, so yeah, that's what I wanted. I wanted to see the graph. Okay, perfect. Moving on. Oh yeah, the interpretation again. So let me say it again. 95 of, if I repeat the experiment 100 times, 95 of those will have the true population mean. So now if I repeat, because I wanted to repeat this for 99%, the interval will be wider. Okay, same interval, but wider. So let's go back to stat. Tests, I want T interval, everything the same. I want the data, but this time I want 99%. It will be a wider interval, and as you see, from 34.651, and you can do that with StatCrunch, 949. So if I want to be higher, if I want to be confident more than 95%, I want 99%. Now I have a slightly different problem, that the interval widens up. So with 95, it's narrower. You can say, oh, okay, with here, not by much. True. But if I'm looking for an estimate, I want to narrow the interval. So I can say it's here. Again, it's not a big deal. It's not a big difference. But that's the difference between 95% and 99%. They can wait. Okay. Finally, I would like to determine the sample size necessary for estimating the population mean with a specific margin of error. Okay. So let's go back. Again, I want to show you how we get that. So we know that the margin of error is T alpha over 2 S divided by the square root of n. And I want to solve the equation for n. Okay. Since n is under the square root, I will have to square both sides. And I have e squared equals T sub alpha over 2 squared times S squared. But when I square the square root of n, I only get n. This is a proportion I can cross multiply. I move n here. So n will be T alpha over 2 S divided by E, everything squared. Because all these are squared, I put them together inside and then I square it outside. You can say, I don't like this. I prefer this. That's fine. T sub alpha over 2 squared times S squared divided by E squared. It's the same thing. Okay, so let's solve this problem. We again consider the problem of estimating the miles per gallon of a 2011 Ford Focus. How large a sample, so that's my question, n equals how much, is required to estimate the mean miles per gallon within 0.5 miles per gallon. So E equals 0.5 with 95% confidence. The sample standard deviation is what we already, I don't need to use this. We have a better estimate. So we have S equals 2.917. And this is not the best estimate. The best estimate will have more, it's not the best approximation. The best approximation will have more decimals than just 3. Okay, so in order to determine n, I have 2.917 squared. I have E in the denominator, which is 0.5, but I have to determine T alpha over 2 for 95 and for degrees of freedom of 15. And we determined it some time ago, didn't we? Was it for this example? No, I guess it was from a different example. So let's determine T. And once we determine T, we just perform this operation and square the final answer. So T alpha over 2 for 95% and with degrees of freedom 15. Again, I'm going to graph it a little bit more in details than the Z distribution. This is again 95%. Again, this is 2.5%. I think we determined it, but anyway. 2.5%, that's okay. We need it again. Let's do it again. So I will determine this. Of course, it will be negative, but I will not, it doesn't matter. I'm going to have to square it, but I would not use the negative. I would use the positive. It doesn't matter. Okay, so inf T, or with StatCrunch, inf T, the area to the left is that, and 15, and yes. Yes, I remember. It was here, right here, under my nose. Negative 2.1314. Good. So that's what I'm going to put in. 2.1314. I multiply this by 2.917. I divide the answer by 0.5, and I square the answer. in parentheses the previous answer, and I want it squared. 154.6, and I have to say 155. So I'm going to write that n is 154.6. So it has to be n 155. Different people giving us different answers about miles per gallon. This is the number of Fords, or what was it? Consumption, or miles per gallon. But this is how I have to survey. I have to survey 155 people owning a Ford 2011, and they have to give me their miles per gallon, etc., etc.